So we're here at the example table, and in this video we're going to be talking about p-series. Before we do that, let's remind ourselves of the integral test. So if we have a continuous, positive, decreasing function f on this interval from 1 to infinity, and we have a series whose terms are the values of f at the integers 1, 2, 3, 4, and so on, then the series, the sum from n equals 1 to infinity of a sub n, converges if this integral from 1 to infinity of f of x dx converges, and it diverges if this integral diverges. Now we're going to use this test to look at a very particular type of series, p-series. Let's introduce this through 3 examples. So first, does the harmonic series, which I'll specify in a moment, does the harmonic series, which is the sum from n equals 1 to infinity of 1 over n, converge? So let's apply the integral test. So we have f of x equal to 1 over x, since this is 1 over n. So the integral from 1 to infinity of 1 over x dx equals, by definition, the limit as b goes to infinity of this integral from 1 to b. And to find that integral, we'll take an antiderivative of 1 over x, so this is, which is natural log. So this is the limit as b goes to infinity of the natural log of x evaluated from 1 to b. Now, natural log of 1 is 0. Natural log of b as b goes to infinity gets larger and larger. So this thing equals infinity. Therefore, by the integral test, the sum from n equals 1 to infinity of 1 over n diverges. Right? This sum diverges because the associated integral diverges. Let's look at another example. Does the series n equals 1 to infinity 1 over n squared converge? Well, we're going to associate it to a very similar integral, this time the integral from 1 to infinity of 1 over x squared dx. And likewise, this is the limit as b goes to infinity of the integral from 1 to b of this expression. So we'll take an antiderivative, and we get negative 1 over x, and we'll evaluate that from 1 to b. Now, as b goes to infinity, negative 1 over b goes to 0. So we're left with 0 minus negative 1 over 1, which is minus negative 1 over 1. This equals 1. So this integral converges, which means, so by the integral test, the sum from n equals 1 to infinity of 1 over n squared converges. Let's do one more example. Let's examine the series 1 over the square root of n. So does this series converge? Once again, we'll associate it with the integral from 1 to infinity, 1 over square root of x dx. This is the limit as b goes to infinity of an antiderivative of this thing. Let's use 2 root x from 1 to b. Now, square root of 1 is just 1. As b goes to infinity, 2 times the square root of b also goes to infinity. So this is infinity. This integral diverges. So by the integral test, the series from n equals 1 to infinity 1 over square root of n diverges. So what do these three examples have in common? Well, in each case, we're looking at we're looking at a series whose terms take on the form 1 over n to the p, where p is some power. In the first example, it was just 1 over n, so p was equal to 1. In the second example, it was 1 over n squared, so p was equal to 2. And in this example, it's 1 over the square root of n, so p is equal to 1/2. But no matter what value p is, we can always use the integral test to determine whether this thing converges or diverges. In fact, we have a special name for these. These are called p-series. So definition, a series of the form sum from n equals 1 to infinity 1 over n to the p is called a p-series. And I'll leave you with an exercise. For what values of p does this series, n equals 1 to infinity, 1 over n to the p, converge? And you should also figure out, as part of this problem, for which values of p this series diverges.